Hey there, welcome to another video. In this video, I'm going to teach you how to convert equations from rectangular equations into polar equations. So stuff with x's and y's into r's and thetas. It should be a pretty fast video, although I always say that and it's never ever true. So it's going to be a horribly long video. Maybe that way it'll be actually a little bit shorter like I really intend. Although I want to go in depth with this stuff so you actually do understand it. So what a rectangular equation refers to is an equation that can be graphed on an xy coordinate plane. So it has x's and y's in it, the two variables that represent our axes. So what's a polar equation? Something in r's and thetas that refer to a polar coordinate system, something with a polar axis and a theta that's referring to that polar axis and a pole, or looks like an origin. So we're going to convert. Basically, we're just changing x's and y's into r's and thetas. Now, why we might want to do that is because sometimes graphing with x's and y's in rectangular coordinates are very nice. Works extremely well for functions. Really good stuff. But for things that aren't functions, like circles, ellipses, other types of curves like cardioids, none of those are functions, they can be easier to graph with polar equations. And so I need to show you how to convert with that. Basically, there's really only two things you do. You find any time that you can get an x squared plus a y squared, replace that with r squared. This is prime. Like, this is what you're looking for all the time. If you can find that, replace that piece with r squared. If not, then replace any extra, additional, or any, if you can't find this, x's and y's with, we've already done this, haven't we? This is how we converted these polar coordinates into rectangular coordinates for points. And, well, wait, if functions are just an infinite collection of points, so all the points that would graph this particular function, or non-function as the case may be, this curve, whether polar or rectangular, then wouldn't converting equations have something to do with the converting of points? We're just doing it once and for all. And that's precisely what we're doing. Instead of converting just one point, we're converting all the points of a function, whether it's a polar function or whether it's a rectangular coordinate function, by translating these functions from rectangular into polar, and later on next video from polar to rectangular. So really just two things that we do. Let's go through, I'll walk you through maybe 4 examples on how we go about doing this. Let's take a look at 2x squared plus 2y squared equals 3. Now, ultimately, what we want to do to convert from rectangular to polar is use this first, use this when we can't. We've already seen that when we were converting points, we're just going to use it here as well. So let's see if we can find x squared plus y squared. If we can, it might involve some factoring, might involve combining like terms, could involve adding or subtracting to both sides of an equation, grouping some things. But we see it right here. If we have 2x squared plus 2y squared and we factor out the 2, we're going to be left with x squared plus y squared. Well, this rectangular equation, which only has x's and y's, there are no r's and thetas, can be nicely factored to provide something that's easily translatable for us. Now, if we do that, and we notice that x squared plus y squared is exactly what the Pythagorean theorem tells us is r squared on a triangle or on a unit circle, then we can make that substitution. So ultimately, look here first, find as many of these as you can, translate them to r squared. So x squared plus y squared, yeah, we can substitute r squared for that. Now, what do you do from there? Solve it for r if you can. And the reason why we might want to do that is because it'll be easier to see what this actually means. So if we divide both sides by 2, and we take a square root, just like we converted our polar points into our rectangular points, or our coordinate systems, and rectangular into polar, we kept the r positive when we converted that way. We said, yeah, we could make it negative, but it's easier to keep a positive r and use the angle to determine where we're at. The same logic applies here. Whether you have a positive r or a negative r, you are actually going to get the same shape here. I won't ruin the spoiler this time. The shape we get does not matter whether you have a positive r or negative, so to keep things nice for us, we're going to keep this a positive r. And if we rationalize by multiplying square root 2 over square root 2, we get r equals square root 6 over 2. Now, what in the world is r equals square root 6 over 2? Well, firstly, does it look a little bit simpler than this? Maybe not if you're not used to polar equations. And we haven't really graphed them yet, but we will. A couple more videos. If you're not really familiar, that looks simpler. There's not as much junk going on, but we don't really understand what it is. Think about what r means. R is a distance from some fixed point, we call it a pole, looks like an origin, out to where the points of your function would be, or the polar function in this case. That would be a constant distance. There's no variable here. A constant distance away from some center point. This is giving us a circle. Wait a minute, r stands for a radius. This says your radius equals square root of 6 over 2. This is a circle with a radius of exactly that. It's just going to give you a circle around the pole. That's all that's going to happen. It says whatever your theta is, there's no place to plug in theta. So whatever your theta is, anywhere around there, it's going to give you a fixed distance, square root 6 over 2. Whatever that is going to be a circle. Now, does it make sense that this is also a circle? Do you remember that circles are x squared plus y squared if you have the same coefficient? We could have divided everything by 2 and got x squared plus y squared equals r squared. This would have been, if I divide by 2, r squared would have been 3 over 2. The square root would be square root 6 over 2. A circle with a radius of square root 6 over 2. Same stuff. If you've ever seen conic sections, I've taught it before, then that gives you a circle. That's kind of interesting. I hope that's interesting. The center would be at the origin, just like this center is at the pole. This is why it's a little bit nicer, is because this acts as a function for us, where this one doesn't. You have to know about conic sections. You don't here. This is a function in terms of polar coordinates with a polar equation. So every single unique theta is going to give you out the same radius. Then every single point around there is one input gives you one output idea. And that's very nice. So this is one reason why we convert into polar. So it makes it a little bit simpler for things that are like circles and ellipses and things like that. It's a little bit easier to graph when you get used to polar equations and polar coordinates. And it lets you deal with functions a little bit nicer. Let's move on to the next one. One of the first things that we do, especially when dealing with things like x squared plus y squared equals x, when we're converting from rectangular equations into polar, we are always looking for this first. If you ever see x squared plus y squared, replace it with r squared. There's very few exceptions to that. Now, what about the things that you can't replace? So x to the first power, or maybe you just have an x squared or a y or an extra somewhere, and you can't factor it. This was nice because you factor out a 2, but let's say you couldn't factor out the 2, then you would have like a 2x squared plus just y squared. This wouldn't work so well. You can't get those coefficients to be the same, so you wouldn't be able to factor it. If that's the case, and this doesn't work for everything that you have, start reverting back to your individual variables. So x squared plus y squared is r squared. I nailed that. But with the x itself, I can't wrap that up in any way, shape, or form with this. This is the nicest one. Then we got to revert to here. So if x is r cosine theta, which we've seen before, we're just going to make that substitution. So now that we've done that, we've actually converted from rectangular into a polar equation. But there's a little more that we can do. And actually, you have some options. If you remember to rectangular equations, like just stuff with x's and y's, normally we can't really divide both sides of an equation by a variable because we start to either lose solutions or we start to deal with some domain problems. And basically the same thing happens here. There is one exception though. A lot of times, textbooks will tell you, ignore the solution of r equals 0. Why? Because then you can divide both sides by r and cancel it out. So if you did that, okay, if I'm allowed to discount the solution of r equals 0, then when I divide both sides, that's gone. We just get r equals cosine theta. We're going to discover in a couple more videos what that actually is, the shape that that creates on the graph. Now, what if you're not allowed to do that? What if it doesn't say that I can ignore that? Well, then you can do a couple other things. You can get everything on one side. Now, that's something we've seen before. We've seen that a lot, in fact, with lots of different equations of get everything on one side and factor. We could totally do that. Then we'd get r squared minus r cosine theta equals 0. If we factor out the r, we really do get to use a zero product property and create two different equations here. R equals 0 or r equals cosine theta. That here is exactly what we got here. The only additional solution would be the single point. Imagine this. If you have a radius of 0, it says, radius 0. You are right at that pole. It's basically it would be the center of a circle with no radius, just a little dot. That's why most textbooks would exclude that and say, don't worry about that, which allows you to divide by r and exclude that one solution. Some don't, and so you'd show both of them, but remember that you do have a couple options here. So let's move on. We've got x squared equals 4y. We're going to go through the same process. That's rectangular. Rectangular means we'll work on a rectangular coordinate system. That's x's and y's. Everything's in terms of x's and y's. Is it a function? Actually, it is a function in terms of y. If you divided both sides by 4, you'd get a parabola. Hopefully you see that. We're going to now write this in as a polar equation and see what exactly this would do. So in order to do that, though, we're looking really at two things. First, look for this. If you have an x squared plus y squared anywhere, you can get that. Make that happen first. If not, replace your x with r cosine theta, your y with r sine theta. I see an x squared, but I don't see a y squared, and I can't make it. And so what happens here is we've got to replace the x with r cosine theta and the y with r sine theta. We've already talked a long time ago about why this works on a unit circle. We're now just using it to transform, translate, or convert. If x is r cosine theta, then x squared is r cosine theta quantity squared. Oh my goodness, do not just square this thing. It happens from time to time, we make little mistakes, but really be conscious that x is r cosine theta. If you're squaring x, you're squaring that whole thing. And 4 stays, but y is r sine theta. It's really nice if you've memorized that cosines with x and sine is with y. That way these work a lot nicer when you're plugging these in. You go, oh yeah, y is just r, and then I know y is associated with sine. X is just r, and well, x is associated with cosine. Now we're going to square the r and square the cosine theta. And again, you do have a couple options. If r is not allowed to be 0, it says just exclude that, you could totally divide by r right now and remove it from your equation. You'd end up getting divide both sides by r, you get r cosine squared theta, you get 4 sine theta. Hopefully you see dividing by r would eliminate one of these r's, one of those r's, and this is what you'd end up getting if you are allowed to exclude the r equals 0. That's a big if. What if you're not? Well, then another thing we can do is see if we can get everything on one side and again factor. So we've just subtracted. Now, some textbooks will say, that's great, that's perfectly fine, just leave it. And you can, I think that's okay. If you need to go a little bit further, you can factor the r. And if you see it, we really do have that two two things, two equations that we could get out of this. R equals 0 and this equals 0. This would give us that really non-circle, sort of a point. The radius of 0 is just going to give you that point along with this thing there. So we could get that. The other thing that we could do from here, if you choose to do this, or if you're allowed to do this, you can solve for r explicitly. A lot of times we like to do that. So if you divide both sides by cosine squared theta, you could leave it like this, unless you really like identities. Then you can separate that cosine squared. What if you wrote this as cosine times cosine? Well, then you'd have 4 sine theta over cosine theta times cosine theta. It's still cosine squared. Yeah, but this is cool because sine theta over cosine theta is tangent, and 1 over cosine theta is secant theta. There's just a number of ways you can go about getting something different because of all the identities that we do have in this. So I hope that makes sense. Ultimately, honestly, as soon as we did this, we converted it from rectangular into polar. That's really all that it takes. Simplifying from there is as a matter of how far you want to go, what's expected of you. I would say minimally you would do this or divide by r if you're allowed to do that. This is okay. Divide both sides is a little bit better. Use identities, that's really up to you. Some people say that's perfectly fine because it's already in sines and cosines, so we're more comfortable with those anyway for graphing. So that's really up to you. What I wouldn't do is just start dividing both sides by r if you're not explicitly told that that r equals 0 is not allowed. So I'd be very careful with that. Let's try a couple more. So how about 2xy equals 1? Again, I'm not seeing any x squared or x squared plus y squared. I can't get that. But every time that we can't do that, just replace your x's and your y's with what they are equal to here. So r cosine theta and r sine theta. So here we get 2x is r cosine theta. Y is r sine theta equal 1. If we multiply through, we're going to get an r squared. Remember, this isn't a distribution concept. You don't have to FOIL or anything. There's no addition, there's no subtraction. You're just multiplying all of these factors, and because we have r times r, you can get r squared. That does leave us with cosine theta sine theta equals 1. Let's go a little bit further. Notice there is no r over here. You cannot divide by r. If you do, you actually lose a solution. R equals 0 if it's allowed. And so be cautious of that. When you end up dividing by that r, you do technically have to write r equals 0 somewhere in there to show that you have that solution. But for here, we can't do that anyway. However, something that we can do, I hope you see this. If we reorder this and put the 2 here and the sine and cosine reversed, so just reassociate it. That is an identity. And occasionally you see these pop up and they're pretty nice. If you have an identity in there, use it. That's fine. This is the double angle for sine. So 2 sine theta cosine theta is sine of 2 theta. I normally write the identity next that we're using, but this is the identity. That's exactly what it is. So we get r squared sine 2 theta equals 1. A lot of times you can just leave it like this. If you're required to solve for r, it would take a little bit more work. You'd have to divide and explicitly solve, but most of the time you're okay writing that. The reason is because this does not even create a function for r. Much like y squared would not create a function in terms of y, this would give you 2 outputs for every input. So I'd feel comfortable just leaving that. Let's go into the next one. So x minus 3 quantity squared plus y squared equals 9. How in the world do we deal with that? I don't see anything. Well, think about what would happen. Instead of just putting in r cosine theta for x and r sine theta for y, what would happen if you were to distribute that? Would you end up getting an x squared plus y squared? If you do, then distribute that. A lot of the times we distribute first before we substitute, just to make sure that we collect all of our x squared and y squareds to make them r squared. So I'm going to choose to distribute that. That'll be x squared minus 6x plus 9. Now, we have a couple things going on. Firstly, our 9s are going to cancel. If I subtract 9 from both sides, we're going to get 0 for those constants. Also, I'm seeing an x squared and a y squared. I'm going to group those. Once we have grouped them, every time you see x squared plus y squared, replace it with r squared. When you're converting from rectangular to polar, that's a great thing to do. So this is r squared. However, this x can't be paired up like that with any other y's. We don't have any other things to pair it up with anyway. It's not being squared. So we have to replace that x with r cosine theta. And we see something that's pretty common when you have these r's. We saw that already. You can factor that. If you added 6r cosine theta on both sides, you could divide by it, as long as you remember that you're removing a solution there. So we want to be very careful when we're doing that. So we end up getting r equals 6 cosine theta. You do have this solution of r equals 0, so be cautious of that. If it's not allowed, you can discount it, and that's just fine. This is really the one that we're looking for anyway, so that's the good one. A lot of textbooks will let you leave it like this. If you want to keep going, this is fine. There's a lot of different options, really. What do I prefer? It kind of depends on what we're doing with it. If we're graphing it, that'd be a lot easier, I'll tell you that. We'd have a point at the center, though, if r is allowed to be 0, so we'd have to be cautious of that. Also, sometimes this is included in there somewhere. So that is something where textbooks don't even care about this because it's oftentimes included. What is this anyway? Well, this is a circle. How do you know it's a circle? That's a circle shifted to the right 3 units with a radius of 3. If you're familiar with your conic sections, that right there is a circle in rectangular coordinates. That has a radius of 3 shifted to the right 3. That circle is going to come back and hit the origin. That's exactly what that's giving you. And so this is included there. In fact, if you take a look at pi over 2 or 3 pi over 2, you're going to hit that 0. And graphically, those would be the same. So let's go ahead and come back with just a couple more examples and then be done. Okay, these really will be quick. I promise, this one time. Why I'm giving these to you is because you're going to find that for a lot of things like normal conic sections, rectangular looks confusing and polar is nice. But for a lot of rectangularly driven functions like constants, like a vertical line or a horizontal line or a diagonal line, like that one with the slope of square root of 3, oftentimes they're about the same, or maybe rectangular is easier. That's really easy to graph. So x equals 3 is a vertical line at x equals 3. Y equals 7 is a horizontal line at y equals 7. Y equals square root of 3x is a diagonal line through the origin with a slope of the square root of 3. Can we convert them to polar? Yes, I'm going to show you how. Sometimes that's valuable if we need to, but a lot of times it kind of depends on what you're doing with it. We won't want to just convert to polar equations just because, if it's already kind of nice to deal with. So if you have to, and you don't have an x squared plus y squared, you just have x and y, convert the x with r cosine theta. Try to solve for r if you can. So if we divide both sides by cosine theta, we end up getting r equals 3. 1 over cosine theta is secant theta. Now, which one's nicer to graph? probably that. But understand this, these will give you the same thing. So if you graph this and you graph this and superimpose the two coordinate systems, so xy plane and the polar plane, they're going to give you the same exact vertical line. It's going to be the same. But hopefully that makes sense that some are easier depending on the context that you're dealing with these in. So with lines and things like that, with normal functions, rectangulars, nice. Conic sections, circles, ellipses, these are nicer. Let's try y equals 7. I don't see a x squared, I don't see a y squared, I don't see them together. All I see is a y. Let's replace it with r sine theta. And if we realize that 1 over sine theta is cosecant theta, this is 7 cosecant theta. So a horizontal line of y equals 7 can be graphed with a polar equation of r equals 7 cosecant theta. Which one's nicer? Again, that one is, if you're just going for the graph, that's probably nicer, but we can convert it. All right, let's try the last one. Y equals square root of 3x. This one's a little tricky, but it's kind of fun. I hope you appreciate it. Check this out. Hopefully it blows your mind. What if we divided both sides by x? Do you remember that tangent theta is y over x? We can replace that. So if we divide both sides by x, we get tangent theta equals square root of 3. So wait a second. If tangent theta equals the square root of 3, theta is tangent inverse of the square root of 3. What's that mean? Tangent inverse of the square root of 3 says what angle gives you out the y divided by x coordinates of square root of 3 over 1, or square root of 3 over 2 over 1/2 if you're looking at the unit circle. That's going to be, let's see, pi over 3. Theta equals pi over 3. Now get this. That's a diagonal line. What's a diagonal line do? A diagonal line maintains the same slope or the same angle in relation to that x-axis. That is the angle. So all this is saying is you have an equation theta equals pi over 3. Just go to the angle. It's going to be all the points along that exact angle, and that would create a diagonal line going through the origin, just like that says. I hope it makes sense. I hope you're seeing it. Kind of did these just for fun so that we could see how vertical, horizontal, and diagonal lines look in polar equations. That one's actually not too bad at all. It kind of shows you the angle at which you draw that line. So I hope I've explained it well enough what you're looking for, when to use the appropriate thing, and how and when you can simplify, especially factoring r, or if you're allowed to divide by r, if r equals 0 is not allowed as a solution. If it is, then you have to show it. Hopefully it makes sense. Next video, we're going to come back and I'm going to talk about how to convert from polar equations back to rectangular. Have a great day.